So we will start implementing in Python now the Bayesian linear regression model. So let's start by importing the necessary libraries. We're gonna need some typing. Okay, so let's do a random seed. I'm gonna use a data set that I will share with you in the description of the video. So for now, I'm gonna load it from the place I have it here. Here's the data. So we are only going to use the X and Y column, right? So let's start doing some standardization. This is going to be the column X dot values, and then we will just subtract the mean and divide by the standard deviation, okay? We're going to work with NumPy arrays and matrices, so we need to add one dimension to X. So we do this by doing reshape. So here we're basically keeping the first dimension and adding one dimension here to the vector, right? And a similar thing with Y. We will read it. And we will use 0, 1 min-max normalization here, because I like to see the prediction variable between 0 and 1. So let's call A and B these ranges. And here we first calculate the relative position of every data point to the current range, and then apply that relative position to the new range. So here we have the relative position to the current range, and we need to apply this relative position to the new range. So we need to multiply this by the new range, which is B minus A, and we need to make sure that this starts from the new minimum of the new range, which is A. And we need to repeat the reshape thing here for Y. So let's take a look at the data. Let's plot this. Okay, so this is the way our data points look like. We can see that here we have a big gap, so we expect to have higher uncertainty in this area for the prediction, right? So we would like to fit a model that somehow captures the patterns, but at the same time is telling us that it's more uncertain in areas where there's not enough information. So let's create our Bayesian linear regression class. So let's assume that the parameters are going to be the kernel parameters, sigma square and alpha square. Let's implement the method that selects the basis for the design matrix. Remember, we need to choose a random number of bases out of the training points. So X is going to be a numpy ND array, and this is going to return another numpy ND array. So here we will first find all the indexes for our training set, and from that set of indexes we will randomly select a given amount of bases. Actually, that's a parameter that will come in the kernel parameters dictionary, and we will use that random selection as our basis to create our design matrix. Okay, X, remember, X are our data inputs. We will randomly choose certain amount of bases, right, out of the set of indexes. So the size of the sample will be part of our parameters. Kernel parameters, let's say that the name of that is going to be number of bases. And this is with no replacement, right? We don't want to give the chances to select one index more than once. And now we just return the training points that have these indexes. Let's implement now the function that creates the design matrix. So this receives the training set and returns an ND array. So we need to capture the number of data points in our training set. We need to capture the number of bases, and then we need to go over each base and compute the exponential kernel between the training point and each of the bases. So we will go over every training point and over every base and compute the exponential kernel of the training point and the base. So let's initialize our phi matrix now. I like to work with the numpy matrices because it's going to be more straightforward to replicate the equations we saw in the slides. Okay, so now we go over every base and compute the kernel for all the training points. First, we need to capture the difference between the training point and the base, and then we need to get the norm of that difference. Remember that the exponential kernel, it's the exponential of minus the norm to the square divided by 2 times the length scale of the kernel, which is a parameter as well. So the first thing we need to do is to capture the difference between the training points and each of the bases. In this case, the base number j. So we are using the norm from NumPy. Here you can see that we have x that goes over every training point, but the base j is just 1. So we will need to replicate the base j to make a direct subtraction between the two matrices. This is going to be kind of like the vectorized version of it. So it's going to be faster. We don't need to iterate over the training points. So in order to repeat the vector as many times as we need, we just need to use the function tile from NumPy. Okay, so we will repeat this base as many times as we need. And how many times we need? We need it to be repeated data point times. And we don't need to repeat it along the columns, just along the rows. So this is the way we use this function. Take a look to this function online to make sure you understand what it's doing. Since we are calculating the norm of row vectors, it means that we need to calculate the norm across the columns. So we need to set the parameter axis as 1. Okay, so we have the difference between the training points and the base j. Now we need to calculate the exponential function of it, exponential kernel. So here we apply minus the difference to the power of 2 divided by 2 times the kernel length scale to the square. And the kernel length scale is going to be another parameter. let's assume it's going to come with that name to the square. And now we can build the column J of our matrix phi, right? We will say that the column J will be this as a column. So we need to transpose it. And now just one more thing, we need to return this matrix, but remember we must attach a column of ones on the left side of the matrix. So we need to use the function hStack. Okay, so now we need to create the fit and predict methods for this class. So X again is going to be an ND array. Same for Y. And this method will not return anything. It's just fitting the model, meaning that here we will calculate all the necessary matrices to compute the posterior predictive later. Okay, so the first thing we need to do is to calculate the basis so we can later build the phi matrix. Now we need to build the phi matrix. We can also use our previous function. Now I would like to define a couple of variables to track the number of bases and number of data points that are going to be necessary for the equations. Say bases. I'm using just capital N here to make the equation easier to read. So the first matrix we need to build here is Vn, which is 1 divided by alpha squared times the identity of the same size of phi plus 1 divided by sigma squared times phi transpose times phi, and the inverse of all that. This plus 1 is because phi has as many columns as the number of bases, but we also have the first column of just ones, right? And the inverse of all this. Now we need to build the matrix M, which is 1 divided by sigma squared times Vn times phi transpose times Y. So let me get this from here. That's all we need for the fit method. Now we need to implement the predict method that will compute the posterior predictive. For the predict method, we need to receive the X star, the input of the new locations where we want to make the predictions. This is again an NumPy ND array. And this method will return two things. One is the mean of the prediction for all these X star locations and the standard deviation that we will use to plot the uncertainty on the predictions. Let's first define a variable that captures the size of the input. In this case is the number of entries in X star. Now we need to compute phi star. For that we can use our create design matrix function, but this time we will receive as an argument X star. Now we need to compute sigma. So for the standard deviation is basically the diagonal of this matrix, but it's square root, right? Because remember that the diagonal of sigma are the variances for all the predictions, and we need the standard deviation. So it's going to be square root of the diagonal. And Y star, which is actually the mean of the prediction, is going to be the product of phi star and M, right? We will plot this prediction, so we need to make sure that it's an array of just one dimension. Let's just return this. So let's create a model. So let's use for kernel parameters a length scale of 0.2, a number of bases, let's say 40. We need to define also sigma square and alpha square. Let's say sigma square is going to be 0.01 and alpha square, say 2. Now we need to run model.fit. And now let's make some predictions. So let's add some new data points to predict. So let's say input size is going to be 500. We will predict across the whole line. Let's say that our x star, we will use numpy line space from the minimum to the maximum of x. Say make sure that it's taking the first dimension. And again, let's treat this as a matrix. Let's try this first. Okay, now we need to call our predict method. So y star and sigma are going to be model.predict x star. So we need to plot here the mean of the prediction, which is y star, and our uncertainty that comes in sigma, right? Let's first plot our training points. Let's use here a color that represents the uncertainty. Now we need to plot the prediction, which is the mean or y star, and the variance. And to plot the variance, usually we use like a color that goes between the mean and one standard deviation. And then we can actually add colors for 2 standard deviations and 3 standard deviations, such that we can have a sense of how the uncertainty goes as we are moving away from the prediction. And to plot that, we use the fill function from matplotlib. So usually we use it this way. So this means that we are walking backwards from the last position, and we are putting together x star like in one direction and the other direction. This is because we are filling with colors over the mean plus 1 sigma and below the mean minus 1 sigma, right? And now we need some parameters like alpha, which is basically the degree of transparency. So 0.2 means that it's 80% transparent. And let's use the filling color. Okay, let's okay, here we go. Usually it looks better when we repeat this 3 times. We will use now 2 standard deviations and then 3 standard deviations. Here you go. So you can see that in areas where we don't have so many data points, or we don't have data points, the uncertainty is bigger. Something we can do to improve this is to make a better selection of the bases, because the basics functions are selected randomly it's very likely that we are not going to select too many basis functions in areas where data points are isolated, like here, for example. So usually a better way to sample the basis functions instead of doing it randomly is to use k-means. Let's say we want to use k-bases to calculate our phi matrix. Instead of randomly selecting k data points from the training set, we can run a k-means with k centers and use the centers as the most representative samples. So for that, we can use k-means from scikit-learn. Let's run that. Let's create a new function here called k-means basis. So here we will run k-means and then return the clusters. The number of clusters is going to be the number of bases. That comes as a parameter. And we will fit this and we will return cluster centers. So now what we can do is, like, depending on another parameter that tells us what kind of sampling method we want to use, we will run one function or the other. So we can create a new function here called create basis. And depending on the kernel parameters, we will run one method or the other. Let's call this basis sampling method. We can call that random. We will return, in this case, the random basis. Then if it's none of them, we will raise an error, right? Let's say sampling method. Another check we must do here is, like, someone can ask to run or to use more bases than the number of training points we have. That would be an error, you know, that we need to make sure that the number of bases is smaller than the number of data points in our training set. So we can do the following. Let's say let's see if it's equal or greater than the number of data points in our training set. Then we will raise an error as well. So now we can run this with our new method here. Let's run k-means. Let me run that again, and now let's plot this prediction. And this is different, you see. The model looks much better, right? We are capturing the variability pattern, and the uncertainty is growing as we move to the areas without data,